The next chapter here is entitled Show Me the Monoid. It's a little bit of a callback there to Jerry Maguire, if you've ever seen that film, Show Me the Money. Show Me the Money was a phrase out of that film. Show Me the Monoid is, it's about abstract algebra. So we're going to cover a few different parts of abstract algebra, moving beyond Algebra 2 into abstract algebra. We're going to show how these are used a whole lot for working with data at scale. So 2014 has been called the year of the monoid. Yeah, frankly, we're just kind of making that up, but we're going to try to circulate the rumor. I think it should be called the year of the monoid. Basically, there's been a lot of talk about monoid this and monoid that, and data scientists at places like LinkedIn and Twitter and eBay and others running around and saying that this is really super important for what we're doing with data. Talking a lot about abstract algebra, about semigroups, abelian groups, etc. Other people who are working with big data are still trying to get their ETL going and pulling in, ingesting a lot of log files. So there's a bit of a discrepancy there between the people who are working with abstract algebra concepts and saying, hey, this gets us great ROI at scale, versus people who are just like chunk through Java code to ingest their log files. I think that's a very interesting thing. What it tells me, and again, I run into this a whole lot when I'm out teaching workshops, what it tells me, though, is that there's definitely a few different camps in big data. And I find that there's a lot of companies who are still just focused on getting their log files in and slicing and dicing those, maybe doing some rollups in log files for their week-over-week reporting. But then there's this other camp of people who are going in and applying very interesting notions out of advanced mathematics to be able to do something more powerful with their data. And again, those are the high ROI apps. And companies that are very exemplary of this would be, for instance, Twitter, eBay, et cetera, where a lot of the really great open source in this area is coming from. And along with that, if you take a look on GitHub, you look at a lot of the open source projects for big data that are popular, you probably notice after a while that functional programming gets called out over and over. So one of the questions here, how come so many open source projects on GitHub use functional programming? We're going to explore that in detail. It's very closely related to the use of abstract algebra. And I find that even a lot of programmers haven't encountered that yet. So it's a good thing to know. And then number 3, I think I answered this already, but who, if anybody, uses abstract algebra in commerce? The answer is it's used a lot. I'm going to assume that people who are viewing this material, generally speaking, there's a lot of need to manage large-scale data and work with analytics at scale. So the following section is going to really emphasize 3 value propositions. Number 1, functional programming. It's a way of mitigating your software engineering costs when you're out there working on really large-scale cluster computing. And it's also very important when you've got interdisciplinary teams, which is generally the case when you're working with data science. Number 2, this is a way of greatly reducing latency in terms of real-time analytics or streaming through petabytes of data. Latency can be a really big problem. And in a lot of businesses, you can actually measure revenue loss in terms of milliseconds. You think about finance and what they're doing on trades. Literally, you can measure how much revenue loss you have as a function of how many milliseconds latency there is in your responses. Number 3, avoiding bottlenecks. Typically, when you're working with batch processing at scale, say you've got Hadoop running on a large cluster and you're working with some 50 terabytes of data, let's say. I'm going to have to adjust that number. The clusters are getting larger, so let's say it's a petabyte of data. One of the problems you typically have is you can encounter bottlenecks as you're processing very large-scale data in batch. And there are reasons for that, but it's because the data is differently shaped. And as it's flowing through the pipelines, you can get some bottlenecks as a result. So these 3 things, software engineering costs, reduced via functional programming, reduced latency, and avoiding bottlenecks. We're going to take a look at these 3 themes over and over. It's really the bottom line for why do you use abstract algebra for big data. First off, though, we need a few more math definitions. So if you want to learn about math, there's a lot of great math papers out there. And there's a nice example of one I like. It's called Introduction to Semigroups and Monoids. It's by Peter Clark down in Atlanta, University of Georgia. And if you follow the link, take a look at the paper, It's got some pretty interesting sections in there. They talk about what is a monoid, what is a ring, what is a group, what is a field. And if you look at what they're coming out with in terms of the math that's expressed, compared to most math papers, I'd say this is a good one. But even this is probably not all that accessible unless people have done, say, graduate level mathematics. So I think it's interesting to try to make this more accessible, try to make it so that the math is not so difficult to read. My co-author and I, Alan, when we were in grad school, here's a cheat sheet that we really could have used. It would have come in quite handy for midterms and problem sets. Basically, we can take a look and say that if we start out with a set of numbers, some non-empty set, doesn't even have to be numbers, but we'll just use those, then we can start attaching more and more detailed properties to these sets. So for instance, if we take a set of numbers and we attach a binary associative operation with closure, we'll get into all those terms. But if we put those properties onto it, then that set turns into something called a semigroup. Now, if we take a semigroup and we attach another property, say that it has an identity element, and we'll get to that in a moment, then instead of a semigroup, it's more specialized. It's a monoid. There's additional things you can do with it. If you were to take and make sure that each element in the monoid has an inverse defined, then we can call it a group, which has even more properties that we can leverage. So on and on, there's kind of a taxonomy of how do you just start out from a whole bunch of numbers and then get more and more refined into different types of definitions that have mathematical properties that you can leverage. That's a cheat sheet. So drilling down into these, first one I'm going to talk about, it's called a semigroup. It's defined as a non-empty set with an associative binary operation. So let's consider an example. Let's just take natural numbers, including 0. So let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the negatives as well. We'll take that as our set, and then for our associative binary operation, we'll use addition. Very simple case, the addition operator. And it's binary and associative. Remember that we were able to say 2 plus 3, quantity, plus 4, is the same as 2 plus quantity, 3 plus 4. They both equal 9, but you can move the parentheses around. That's associative. And we know that 2 plus 3, we know that the plus operator is binary. It takes 2 operands. So we've got an associative binary operation. Also, the number that you get out of 2 plus 3 plus 4 is 9. That is also inside the same set, natural numbers, including 0. So we can say that we have a property of closure, that if we take and pull out some numbers from our set, apply this operation to them, we get another number that's still a member of that set. There's some closure in there. Great. So that was called a semigroup, and we encounter that a whole lot when we're working with data at scale. Now, if we take and refine this idea a little bit further, we take a semigroup and we can add to it another property. That is to say that there's an identity element. Okay, so if we've got a semigroup with an identity element, then we can call it a monoid. Now, in our example of the set of natural numbers and the addition operator, the number 0 works pretty well. So if you take 2 plus 0, you end up with 2. That is to say that the number 0 is your identity element for addition. You know, using integers for examples here, frankly, the mathematicians would probably say that's not ideal. Integers have other properties, and we don't want to mix it all up and confuse it. But I think it works pretty well for the examples that we have here for now. Let's just say that they don't have to be numbers. Okay. Another type of thing that we examine is called a ring. And that is if we start out with a semigroup and we have 2 binary associative operations, we'll say both addition and multiplication. So if we have those 2 additional operations, we can start to call it a ring, which has other properties we can use. Now, we could keep going as far as that whole taxonomy of semigroups and rings and monoids and groups and fields, et cetera, et cetera. There's an even broader category that's called a magma. I always thought that magma was lava, but apparently there's a larger field of this that's entitled a magma. We could go through concise definitions for all of these, but let's just not. Instead, let's consider, we've been discussing about sets. We've been discussing about what we can do with the elements of particular sets. And we can have these descriptions, semigroups, monoids, groups, rings, etc. They could be elements of sets of numbers, for instance. Or you replace it, and instead of having numbers, you could have sets of vectors, or sets of matrices, or sets of tensors, or polynomials, circulants. You can go on and on. There's a lot of different kinds of things in math that could be represented as sets. And remember before, we were talking about polynomials, where you could take one polynomial, add it to another, and you end up with a third polynomial. So that's great. It kind of tends to imply that the polynomials, adding them together, we could describe that as a monoid. And so, question there, what would the identity element be? Essentially, again, 0. So what I want to throw out there is an idea, kind of a bold idea, but what if, in the context of these semigroups, rather than talking about numbers, what if instead we were talking about chunks of code? So we could be describing, say, objects in some programming language. And we could operate on them with, again, these same kind of properties of like associative binary operations and identity elements, etc. And taking this idea a little bit further, remember we talked about variables in equations. We talked about variables being algebraic numbers. So to get a little bit more abstract, ergo the name abstract algebra, what if the variables actually represented the operations instead of the numbers? If the variables represented operations on things, we can do a lot more interesting stuff. And that really cuts to the chase of what you're doing with all these semigroups, monoids, etc. Now, an interesting thing is that when you're working with big data and you take a look at the code that people write, they're in many ways probably already exploiting this notion of semigroups and abstract algebra, probably without realizing it. I tend to find that a lot of big data developers don't know what the math names are for the kind of code that they're writing. And there's a downside to that. They can't describe the math that they're actually leveraging or know how to recognize those patterns and be able to generalize out and build algorithms by recognizing patterns. Getting back to computational thinking. So what we want to try to push towards is exploring why you would use semigroups, how this really comes into practice. But again, in terms of computational thinking, we're trying to stress here a couple of points. One is decomposition. So we can say that algebra, instead of operating on numbers, we're going to operate on functions. Okay, that's a way of computing about programs. Another way of saying it is code as data. You definitely see that in functional programming, especially in Clojure. We talk a lot about code as data. But that's what we're doing here. What that means is that by applying a lot of this abstract algebra to your functional programming code, then you can let the compilers do a lot more interesting things for parallel processing. And that's the big win, is can you get small little sections of code that operate on ginormous clusters and run with petabytes of data very efficiently in parallel. That's what we're trying to cut to. The other thing is more of an engineering argument, software engineering argument, and it has to do with pattern recognition. So if we can begin to recognize when there's a semigroup, that kind of structure in what we're doing, take a look at the business logic of what we're implementing in a workflow, for instance, then we can start to build out code libraries based on monoids and things like this. Code libraries that operate on a very wide variety of different types of structured data. Could be polynomials, could be matrices, could be graphs, etc. But it's just a placeholder. So we can apply the same code to a lot of different types and shapes of data. And also, by extension, we can operate on a whole bunch of different types of system architecture underneath. We can run the same code on, say, Hadoop or on Storm or on Spark or other things, but just be able to use these code libraries over and over. So that leads to greater code reuse. From a software engineering perspective, speaking as putting on my engineering director hat, it means much less code that we have to test and debug. And when you're working at scale, that's a big problem. It's usually your biggest problem at scale.